Daria Sokhan, University Lecturer of Physics. Hello, I'm an experimental hadron physicist, which means that I'm fascinated by and study the nature of hadrons. These are the particles which make up almost all of the visible matter in the universe. You probably know the most famous members of the group, protons and neutrons, which form the atomic nucleus. They themselves, however, are formed of quarks, held together through the exchange of gluons. It is the quarks and gluons which are the truly fundamental constituents of all visible matter from faraway galaxies to you and me. Quarks come in different flavors and combine in different ways to produce a multitude of particles called hadrons. Almost all of these are extremely short-lived and here on Earth can only be produced in high-energy collisions, for example in particle accelerators. We study the forces by which the quarks and gluons are governed to understand how and why protons, neutrons, and nuclei are formed, which in turn gives us the key to the formation of stars and galaxies. It also allows us to look back in time, right to the earliest moments of the universe, to understand some of the first steps in its formation. What makes the puzzle of quarks and gluons particularly tricky is that we cannot isolate a single quark and study it. They only occur within hadrons or in an extremely hot state called a plasma. This makes experimental hadron physics extremely interesting, but also extremely challenging. I'm a lecturer at the University of Glasgow, but my research is carried out within a large collaboration of international scientists at Jefferson Laboratory, Virginia, in the USA. And I'd love to tell you about our experiments and what we're learning about the inner life of the proton. At the laboratory, we accelerate the electrons to extremely high energies and collide them with stationary targets composed of different nuclei. The electrons have so much energy that some of them penetrate inside the proton and scatter from the quarks inside it. Often the quarks are knocked out and form other hadrons as they fly out. From there on, it's detective work. We detect and measure all of these particles and reconstruct what must have happened in the interaction, testing different theories. The accelerator is like a giant microscope which allows us to look right inside the proton and map out its internal dynamics.